Okay, good morning, students. So we'll start the session. So I hope you have seen first lecture that I sent a message yesterday. You have to watch that lecture because which is helpful to understand the other concept. So I hope all you have seen the first lecture for unit number 4, in which I have discussed IPv4 address. What is address space? Address space is nothing but the total number of addresses you will get in the IPv4 address. IPv4 address size is a 32-bit. Obviously, it is providing you the 32-bit different combination. Like 0, 1, 2 bits are there. So two combination, how many different combinations will provided by the 2 bits 0, 1? Definitely 2 raised to 2. That is 4 combination 0, 0, 1, 0, 1, 1. Similarly, 32 bits are there, so you will get the 4 billion combination. So we have seen how the addresses are divided in classful addressing in different classes. And in the classful addressing, the major problem is address depreciation. Address depreciation, that is nothing but the wastage of addresses we have seen in the last recorded lecture. So address depreciation means the wastage of address. So in classful addressing, the number of addresses were wastage. So the next solution we have seen, that is classless addressing. In classless addressing, we can provide the addresses as per the entity requirement, as per the customer requirement. For example, if the customer wants 3 addresses, yes, we can provide the 4, the 4 addresses, because the address must be power of 2, it must be contiguous. Right? We have seen the restriction. Here is also one address is vesting, but the compared to the classful addressing, in classful addressing you have to allocate the class C address. It means 256 addresses. And if the customer wants only 3 address, around 253 addresses were going to waste. But in classless addressing, only one address is going to waste. We have seen the different short-term solution, subnetting, supernetting for the classful addressing, as well as network address translation. The network address translation, you have to watch on through the YouTube what is the concept of network address translation. The network address translation is used in our college because we have taken one lease line from the BSNL. So we have only one IP address. But still, we can provide internet connection on hundreds of kilometers. How it is possible? It is possible because of network address translation. Network address translation is also one temporary solution for the IPv4 addressing, by which having one address in the organization, you can provide internet connection on hundreds or thousands of computers. So this is one again solution. Okay. So all these things I have covered in the last lecture. So today we'll start IPv6 addresses. So this is one assignment for you. Watch the concept of network address translation on YouTube. So we'll see how many participants join for the session. Around 39 participants are there. So from tomorrow, you should present sharp at 9 a.m. and I will take your attendance at in between the session anytime. So you should present for the session, uh, the whole session, so that your attendance will be marked. So today we'll see the concept of IPv6 addresses. So we have seen IPv4 address provides you 4 billion addresses. But today, if you see the internet requirement, day by day, the number of users are increases. We have seen on one mobile phone that two SIM cards are available, and on both the SIM cards you can use internet. In one family, there are 3 to 4 on an average mobile phones are there, and on every mobile phone the two SIM cards are available. So, and you can use internet connection on every SIM card. Now imagine how many IP addresses are required, because gradually, day by day, the number of users are increasing. As well, the number of IP addresses are required, because we have seen in last lecture, unique address required. If you want an internet connection, universally unique address required. Then only the packet will be routed to your device. So, and IPv4 addressing, the problem is address depreciation. Depreciation means the number of address were wastage. Even though there is a classful addressing, in the address wastage problem are there. Similarly, classless addressing, there is a address wastage problem is there. So we've seen different solution like network address translator, subnetting, supernetting. So despite of these different short-term solution, this depreciation is still long-term problem for the internet. So the solution is IPv6 addressing. So it is in IPv6 addressing, IPv6 address is a 120 long. So we have seen IP addresses 120 32-bit long. So from the 32-bit, you will get how many addresses? 2 raised to 32. So means around 4 billion combination, 2 raised to n. So here IPv6 address is a 128-bit long. So how many addresses you will get from the IPv6? 2 raised to 128. So huge number of addresses are available. So address space is very big compared to the IPv4 addressing. We have seen in IPv4 address, the notation is binary notation and decimal notation. But in 32-bit, binary notation is possible. It is difficult, but still it is possible. You can read a 32-bit binary bit. But 128-bit, it is very difficult. So IPv6 addressing, there is no binary notation, nor decimal notation. For the 128-bit, we use hexadecimal colon notation. Hexadecimal colon notation. So 128 bits are there. These 128 bits we can represent by the 16 bytes. 1 byte, so 16 bytes is equals to 32 hexadecimal digit. So these 32 hexadecimal digit are separated by the colon. So here you will see there is 8 blocks are there, and these 8 blocks are separated by the colon. And in each block, there is a 4 hexadecimal number. So 4 hexadecimal, so in this way, we can represent IPv6 address. Now, this 128 bits, it means 128 different combination. So the first combination, like 127 bits are 0 and 128 bits is 1. Is one combination. So here you will find almost all the bits are 0, only the last bit is 1. This is one address. This is one combination. But it is very long to write. So what we can do, we can minimize the address That is the abbreviation. So that in a very less space, we can write the address. It is easy to read. It is easy to write. But how we can abbreviate the address? So here in the example, the original address, here you will find there is a 8 box which is separated by the colon. Now here you have to see if there is a contiguous 0. So here the third, fourth, fifth block, there is a contiguous 0. So instead of 40 in abbreviated address, we can write, instead of 40 we write only 10. So the first block FDEC colon 74. So here again you have to see 0074, instead of 00 we are writing only the 74. So this 00 the beginning 00 is not valuable. We can drop this 00, right? Like if we are writing 9 and 09, so we can drop 0. It does not affect the value. So like here, the 4 zeros are there. Instead of 40, we are writing only 10. So these two rules that you have to remember. If there is a leading 0, which are not adding any value, we can drop in abbreviation. So here the 3 leading zeros are there, we can drop. So 0, again B0FF. Again, there's a 3 we can drop, triple F 0. Now, in more abbreviated, if there is a continuous 0, we can represent this continuous 0 by the gap. Like here, the third, fourth, fifth block, you will find there is a 0 colon 0 colon 0. So instead of this 0 0 0, we can represent by the gap. Now here is one question. Like suppose if left side there is a 3 0 colon 0 colon 0, and then value is B0FF, and at the right side there is a 2 0 colon 0 colon 0. So that time how many time you will represent a gap? Only represent a gap. If even though instead of this 0 triple F 0, instead of this last box I'm talking about, if triple F 0, instead of this value, if there would be 0, but still you can represent gap only one time, because again you have to write original address from the more abbreviated address. So if the gap you are representing two times in the address, it will get confused how many zeros in between the gap. But here you can easily identify how many zeros are here. Like if you see the more abbreviated address, FDC is one block, 74 is a two block, B0FF is a three block, 0 is a fourth block, and triple F 0 is a 5 block. So 5 block uh, are present in a more abbreviated address. So in a gap, definitely there will be the 3 block, and all the 3 blocks are zeros. You can easily identify it by the gap. If there is a 2 times gap, you cannot identify how many zeros in first block gap and how many zeros in the second gap. So this is a very simple problem. You may ask to write abbreviated address from the original address. Okay. So now we'll see the IPv4 address datagram. IPv4 datagram. This IPv4 datagram is nothing but the IPv4 packet format. So IPv4 is in the network layer, as we have seen in our previous lecture. The major role and responsibilities of network layer are routing, addressing. So addressing part we have seen, like IPv4 address is there, IPv6 address is there, which is used to identify the destination and the source machine, as well as the routing. That is the another responsibility. So what is the routing? Whenever datagram received to the router open a datagram and he will get the information from the datagram or the packet, and based on that information, the router consult with the routing table and forward a packet through the respective node or through the respective path. Now we'll see the IPv4 datagram. So in IPv4 datagram, here you will see the header size is a vary, which is 20 to 60 byte. So header in IPv4, header is not fixed. Here the header size is a vary in between 20 to 60 byte. And data size is again it vary, which is in between 20 to 65,536 byte. Again, the data size is not fixed. It will vary in between 20 to 65,536 byte. So we'll see what are the information in header which is required for the routing. So here you will see the information is like version, VER for the version. So 4-bit define the version. Like we have seen two versions, IPv4 and. So this first field, which tells to the router, the destination host or computer or node, the received datagram is IPv4 datagram or IPv6 datagram. The second 4 byte is to remember header length. So this 4-bit define the size of header, because the size of header is vary in between 20 to 60 byte. You can write 20 value with the 4-bit. With the 4-bit, you can write up to the 15. If the all 4 bits are 1, then maximum 6, you can write up to the 16. So whatever header length, which is multiplied by 4, which is multiplied by this way, we can calculate the size of header. The next 8-bit define the service. So there is IPv4 protocol. So first service is a service, and the second one is first service, and second one is differentiated service. So here 8-bit. So out of 8-bit, the first 3 bits are precedent and are providing a type of service. What type of service is going to provide the. So D stand for minimize delay, T is for R is maximize reliability, and C is minimize the cost. And precedence defines the priority of datagram in issues such as congestion. Because at the time of congestion, the router has to take a decision. If the priority is more, the router allow a datagram to route in the network before than the other datagram. So the router will take a decision at the time of congestion which packets are discarded and which packets are allowed in the network. So precedence tells us the importance of the packet. Now minimize the delay. Minimize delay, maximize reliability. Now minimize delay. When this minimize delay is required? When you are chatting with your friend When you're chatting with your friend, that time you are attending the chat, attending a response, whatever you minimize data services required because user is waiting for the reply. Throughput. When the maximized throughput will be required, where if you are downloading a data from the internet, that time also you will wait to. So if you are downloading data, that time T will be enabled because the maximized throughput you will get. You want a maximum output, maximize reliability. Now, when the maximize reliability means reliably your packet must be reached to a destination. So reliability is more important. So when such kind of packets required, these packets required for the network management. When you are managing a network, uh, there is a different protocol who share different types of packets to manage a network. Like in this unit, we'll see like distance vector routing protocol, link state routing protocol, like RI or SPF, which share a routing table information with the other routers. So these are the different managing protocol. So which share information to the router to manage a network. So in such type of datagram, the reliability is more important. Min cost. Minimize the cost. This type of service required whenever you are reading e-newspaper. So in e-newspaper, you are not always look for the latest news. You simply read the news, and whenever anything happen all the world, automatically the news will be added in the e-news, right? So such type of traffic minimize the cost because user is not attending continuously, is not waiting for the new news. Anything is happen, it will automatically added and the user will read. So that time minimize cost service required. So all in this service, that is type of service, and the second one is differentiated service. So in differentiated service, the first 6 bit tells you the code point and 2 bits are never used. So here 4 bits, sorry, 6 bits. This 6 bit, so in the type of service we have seen 4 bit tells you a different, provides different services like minimize cost, maximize real. These different protocol uses these different types of services. Okay, I'm talking about differentiated service. So in differentiated service, the first 6 bit define the service. So basically, these 64 services are there. So in the 64 services, these 64 services are divided into 3 categories: internet, local, temporary, or experimental. So out of the 3 category, the 1 bit, the last 1 bit, if the last 1 bit from the 6 bit, the last 1 bit is 0, it tells us all these services are internet services. So from the 6 bit, if 1 bit, which is used to identify the category, the remaining 5. So from the 5 bit, how many services you can represent? 32. So 32 bits, 32 services are available for the internet. Again, for the local, last 2 1 bits represent the category. If the last 2 bits are 1 1, which shows local service. So remaining bits are 4. So from the 4 bits, 16 different services are available for the local. And similarly, the third one, that is temporary or experimental, 16 services are available for the temporary or experimental. Okay. So we'll see. We have seen version, IPv4 or IPv6, length 20 or 60 bytes, service, that is type of service and service. Now the 16-bit tell us the total length of datagram. It means the header plus data. Now why this field is required? By this field, the router or the destination host will come to know the size of data because he can easily calculate the size of data from the total length. Size of data is equal to total length minus header length, by which he can easily get the size of data. So 16-bit. So from this, by the 16-bit, how many bytes you can represent? Obviously 65,536 bytes because 2 raised to 16. 65,536. Okay. The next field is identification, flags, and fragmentation offset. So I will cover this field later in today's lecture only. We'll remember identification, flags, and fragmentation offset. All are related to the fragmentation offset. That's why I will cover this triple letter. Now the next field is time to live. So here 8-bit define time to live. Okay. So time to live. Time to live means the survival time of a datagram in the network. For how much? For how much the packet will be survive in the network. Now why this field required? Now imagine if when the datagram moving into the network, if the two router tables are corrupted and the one router is sending a datagram to the another router whose routing table is corrupted, and that router again sending a datagram to the previous router, again his routing table is also corrupted. What will happen? Your datagram is moving in between two routers only, and the destination computer is waiting for the datagram, right? So you have to decide when the datagram will be discarded and informed to the source. This datagram is discarded because the routing table is corrupted, and so that the source will send a packet with the another path. Otherwise, the same will happen. The source again will send to whose routing table is corrupted, and the packet move in between the two routers only. Right? And again, the destination machine will wait for the packet. Okay, so to solve this issue, to solve this, initially this time to live field is designed to hold a timestamp, and this timestamp which was decremented by each visited router. So timestamp, and whenever the packet moving from the router, this timestamp is decremented as soon as the packet moving from the each router. And whenever the timestamp is 0, and if the packet is not received to the destination, the router simply discard the packet and inform to the source. The packet discarded because time to stamp 0. But today, this field is used mostly to control the maximum number of hoops visited by the datagram. So here, the source added the total number of router datagram has to visit to reach a destination. For example, source to destination, the datagram has to visit 4 routers. The source added 8 value from the step side instead. he add double value like a, because in between 8 router, the packet must reach to a, the router has to visit four, sorry, the packet has to visit the 4 router only. But the safe side, the source is adding 8 value. In between 8 router, the packet must reach to a destination. Okay, so this time to live field is required because routing table in the internet can be corrupted. The next field is a protocol. So this protocol will define which higher layer protocol using this IPv4 service. So in network layer protocol, there is ICMP protocol, Internet Control Management Protocol, IGMP protocol, Internet Group Management Protocol, OSPF protocol, Open Shortest Path Bus protocol. These are the network layer protocol, as well as the transport layer protocol like TCP, UDP, SCTP. These different protocol uses a network layer services. So the router as well as the destination host should come to know which lay a protocol using this service. As per the protocol, a different value is added in the protocol field. If you are using ICMP, the value would be 1. If you are using IGMP, the value would be 2, and so forth, like TCP, UDP, OSP. The next field is a checksum. So in our previous lecture, we have seen what is the use of checksum, how we can identify the error through the checksum. So checksum is used to identify is there any error is occur in IPv4 datagram or not. Source address. So this 32-bit define the source computer address, sender address, and the destination address. The next 32-bit define the destination address, that the receiver computer address. Okay. In this problem, IPv4 packet has arrived with the first 8 bits as shown. So one IPv4 packet is arrived, and the first 8 bits are 01, then 000010. Now the receiver discard the packet Y. First bit is version, and 4-bit define the version. So the first 4 bit, like 0100, that is the value of 4, 1, 2, 4, right? So for the first 4-bit, define the 4 value. It means the received datagram is IPv4 datagram. The receiver computer can easily come to know. But the next field is version. The second one is header length. And in the header length, the value is 1, 2. So value is 2. So as we have discussed earlier, whatever value is there in the header length field, which is multiplied by 4. Because you cannot write a 60 value in 4-bit. So if you can write 15. So 15 into 4, that is 60. So only the 4 bits are there. So you have to multiply with the 4. So here is a 2 value. So 2 into 4, that is 8. But we have seen the minimum header size of IPv4 is 20 to 60 byte. Here, this datagram is telling 8 byte, which is wrong. The header size must be 20. So what it mean? It means the packet is corrupted in the transmission. This value change in the transmission, and that's why the receiver discard the packet. So very simple problem. So the 3 fields are remaining, that is identification, flags, and fragmentation offset. Now we'll see all these three fields. Okay, so we'll start with the fragmentation. What is mean by fragmentation? Means divide the packet into different parts. Why? What is the necessity? We have to divide the packet because there is a different types of network. We have seen a different types of network, and each a different type of network having its own maximum transmission unit, that is MTU. We have seen FDDI, Ethernet, X.25, right? In our previous lectures. So actually, these different types of network having different maximum transmission unit. Why the different types of maximum transmission unit? Because different types of protocol are used in the different types of network. Like in Ethernet, we have seen we use CSMA protocol and the CSMA protocol to identify the collision. Minimum size is 1500 bytes. So there is a different maximum transmission unit for the different type of network. But to get efficient, effective data delivery, decided to keep size of the datagram, which is around 65,530. So that is, he has taken a maximum size so that effectively the whole data will be delivered or maximum data will be delivered to the IPv4. But many times, whenever the datagram is moving into the network, he has to move through a different types of network, different types of channel. So in different types of network having different types of maximum transmission unit, therefore we have to divide the datagram into a different parts. Okay, so you are dividing it into a different part is nothing but the fragmentation. Okay. Now the second phase is identification. Now suppose if you are dividing one datagram into three parts. So whenever these three parts receive to the destination machine, the destination machine has to recollect all the three parts, combine together and pass these combined datagram to the upper layer, right? How he will come to know all these three parts are fragmented from this datagram. So for that purpose, identification field is required. By the identification, we'll come to know all these parts are belong to this datagram only. So how the destination machine identify the different parts, the fragmented parts by the two field, that is the source IPv4 address, and the second one is identification value. So this 16-bit field define the datagram originating from the source. So identification and the IPv4 address uniquely define the datagram. And how the identification value is added whenever the datagram forwarded, there is a counter. The counter value is copied into the datagram. And this counter is incremented by the 1. So whenever so sending datagram, the counter copy value into the identification field 56 like this. And if you a datagram whose identification value is 4, so you are dividing this datagram into the three parts. So in all three parts, the value would be the same, that is 4, 4, 4. And these three parts will receive to the destination machine, the destination machine can easily identify because of all the three parts belongs the same value, that is a 4. It means all these three datagram are the parts of the same datagram whose identification value is a 4. So the combination of source IPv4 address and this identification value, the receiver can recollect all the fragmented parts. So fragmentation we have seen, identification we have seen. Now the third is that is a flag. So in a flag, the 3-bit define the flag. The first bit is not used from the flag. The next D and M bit. Now D is for do not fragment and M is for more fragment. So if is equal to 1, it means datagram must not fragment. It means it many times cannot fragment every datagram into a different parts. There are many different types of datagram which cannot be fragmented. And in that case, source keep this value as a 1. And whenever such datagram received to the router and router cannot forward this datagram without fragmentation, that time and if the t is equal to 1, the router discard the datagram and send ICMP error message to the source because fragmentation is not possible. And d is equal to 0, it means datagram can fragment if necessary. And if d is equal to 0, it means yes, you can fragment, you can divide a datagram into the parts. M means more fragment. More fragment. This field is required for the destination machine because destination machine is waiting for the fragmented parts, right? For example, as if we consider previous datagram, you have divided into 3 parts. Of the 3 parts, if the receiver received the first part, is again waiting for the second part, he received the third part, he may wait for the fourth part also, no? Because he don't know how many parts you have divided a datagram. So these more fragment tell us to the receiver machine how many more fragment parts are remaining, which is to be received from the source or the router. So if m is equal to 1, means datagram is not last fragment. So whenever the first part received, m, the value would be m is equal to 1. When the second part is received, value would be m equal to 1. But when the third part received, that time value will be m equal to 0. And the receiver will come to know this will be this is the last part of the datagram. And he recollect all the 3 fragmented parts, combined together and send it to the upper layer. So this is the D and M flag. So you have to remember D means do not fragment, M means more fragment. Now the fragmentation offset. So flags and fragmentation offset both are combined together. So here fragmentation offset, how this value is added and what is the use of fragmentation offset. So here if you see this one datagram, the size of 4000 bytes of datagram. Now this datagram is divided into a 3 part. In the 3 part, the first part 1400 bytes of data are added in first. Again, the second part, again 1400 bytes of data is added, and in third data is added. Okay. The offset by the first byte number by the 8. Now in first part, the first sequence 000, so it is divided by 8, you will get the fragmentation offset value 0. Is 100. So which is divided by 8, you will get a fragmentation offset value that is 175. In third part, the sequence number is 2800, again which is divided by 8, you will get the offset value that is 350. So here you have to remember how to calculate the offset value. And by this offset value only, the receiver computer can identify the first part, second part, third part, and can easily combine together. Here is the example of datagram fragmentation. So different fields we have seen, like this version, the second one is header length, third one is total length, sorry, service, and fourth field is total length. It is 4020. It means 4000 is the bytes of data and 20 is the header size. So total length is 4020. Identification value 1567 is identification value. And the three flag, first is reserved, second one is D, and third one is M. That is more fragment. And the next 3-bit 000 is nothing but the fragmentation offset. So this is the first datagram. Again, this datagram is divided into 3 parts. So see how many fields are going to change. The total length, when you divide a datagram into 3 parts, this datagram size is 1400 bytes and the size of header that is 20. So total length is 1420. Identification value would be the same. See, in all fragmented part, identification value is same. That is 14,567. Again, if you see the flag, in the first part, M is equal to 1. That is, yes, more fragments are available. Again, the second part, M is equal to 1. Yes, again, the third part is available. Then M equal to 0. It means there is no more fragmented part. And again, total length is vary in third fragmented part. Fragmentation offset, the first byte divided by 800, and the second fragmented part, the first byte 1400 divided by 8, that is 175, and third you will get the 350. So in this way, value changes when you divide one IPv4 datagram into a different fragmentation offset. Now we'll see few problems which are very simple. Understand this complete IPv4 packet format. Okay, so first problem, a packet has arrived with an m-bit value of 0. Is this the last fragment or middle fragment? Do we know if the packet was fragmented? The answer is very simple. M is equal to M is more fragment. M is equal to 1. It means yes, more fragments are available. M equal to 0 means no more fragments are available. Right? So this is not the first fragment. Right? Definitely this would be the last one. The M. Next problem, a packet has arrived with an m-bit value of 1. Is this the first fragment, the last fragment, or middle fragment? Now here m is equal to 1. M is equal to 1 means the more fragment parts are available. So it can be 1, it can be the first fragment or middle fragment, but definitely the last fragment. We cannot identify this would be the first fragment or middle fragment because the offset value is not given. So similarly, all these problems will be uploaded through the Moodle. You have to solve this problem. Okay. The next. Now we have seen how the checksum value is calculated. Initially, the checksum value is 0. The all fields are added. The entire field are divided into the 16-bit session. See here the example. Entire fields are divided into 16-bit session. So initially here you will see checksum values are zeros, and all the entire fields are divided into 16-bit session. You have to take an addition and you have to take complement. You will get the checksum value. So the summation of all the 16-bit sessions values, the complement is taken, and here get the checksum value. This checksum value is added into the checksum field for the error detection. Is remaining, that is option. So as we have seen, the header size is vary in between 20 to 60 byte. So if the header size is at 20, it means option field is not available. If it is in between 20 to 40, or sorry, 20 to 60, it means the option field is available. So this option field is used for the network testing and debugging. You have seen a different command like ping command. So this command uses this option field. Okay, so obviously, the command is used for the networking is working properly or not. So the option field having two types, single byte and multiple byte. A single byte having two types, no operation, end of option. No operation means it does not having any use, and end of option, this uh, single byte is using as a filling option, like a padding. It is simply adding 1 byte of data. That is single byte. And second is a multiple byte. And different types are record root, strict source root, loser source root, and timestamp. So you can easily understand their purposes by the name only. Record means whenever datagram moving from a different router, he will record the different router addresses. So it can be listed up to 9 router addresses. Which route datagram is following will be recorded in the option page. Next one is strict source route. Strict source route means whenever packet moving, a packet should follow the same route that is defined into the option field. Transmitted. You are not expecting the packet should move through the network. Maybe the stolen by take into advantage of that information. So you will define a strict source route. So in that case, the packet visit any other router with field, that packet will be discarded. So use the source to predetermine route for the datagram as it travels through the internet. Loose means each router in the list, but datagram can visit other routers as well. So in loose source route, whatever the router addresses you have defined, the datagram must be visited all the routers, but he can visit the others other router to the datagram will not discard it like strict source root. The time which is required in so, so here tomorrow we'll start the next session or be present sharp at 9 o'clock. Uh, if you have, if you could not understand me through the personal chat, uh, session understandable or not, my voice is able to listen or not. Anything if you want to share, you can share all this information with me. And I'm planning to unit number 4 within next 4 to 5. Then next 4 to 5 session, I will cover this complete unit. Just a minute, I am taking participant attendance. Today, actually, my computer is not working, so unable to conduct this session. Okay, thank you, participant. Share your feedback through personal chat. Not all, but few students. Uh, can you understand today's session or not? This feedback really helpful for me to deliver my next sessions so that it will be helpful to you as well as me. So kindly, few students share feedback as well as I will share this problem with you. You should try to solve this problem. And if you have any doubt, any query in this problem, you can ask me through the personal chat. I can share this solution. I can share the problem solution, or I can discuss with you how you will get the solution of this problem. Thank you. You can leave the session.